Today's lesson is how to use a ratio table to solve multiplication problems. Now, tables are a useful way of organizing information. We use them in science. In fact, in class we've used T-tables to keep track of our information and our data, and we'll be able to use tables in math as well. Think of a ratio table as a way of organizing number strings. We've learned about number strings before, how you can use a string of numbers and a string of multiplication facts that are friendly to help you solve a rather unfriendly multiplication problem, like the following. 56 times 72. Yuck. Okay, so how could we solve this with a ratio table? Because of the commutative property of multiplication, we know that we will get this same final answer even if we flip-flop the factors. So we could either think of this as 56 72 times, so basically 72 groups of 56, or we can think of this as 72 repeated 56 times, or 56 groups of 72. We can try it both ways, and we can compare the two problems. So let's start with this first way. 56 72 times. So let's set up a table for ourselves, where the top of the table is going to represent the number of groups that we have, and the bottom of the table is going to represent the total amount that is in those groups. It doesn't really matter which one you do on top and which one you do on bottom, but for the sake of being able to check over your work and to compare each other's notes, let's always set it up like this. Number of groups on top and the total amount on the bottom. So, okay, 56 times 72, yuck. But do I know what one group of 56 has? Yeah, 56. Awesome. Well, could I double that? Two groups would then be 50 times 2 is 100, and 6 times 2 is 12, so that would be 112. Let's do 10. 10 groups of 56? Well, we're basically just placing a 0 at the end because of our place value patterns that we know about. And what about 5 groups? Think of it like this. If I have 10, and that gets me to 5, then I can do the same thing to the bottom. I can have 560, or I can find out what half of 560 is. Well, half of 500 is 250. Half of 60 is 30. So put them together. 250 and 30. And get 280. Now these four numbers here, 1, 2, 10, 5, this is what we can call the core 4. This can be our first 4 moves on the ratio table whenever you are doing a ratio table. So that way, if you're not quite sure where to start here, because why not? Those are usually pretty friendly and quick things to do. So make sure you write down what the core 4 are. Sometimes ratio tables can be intimidating because it's like, ugh, where do I even start? Start with the core 4 and then see what you've got to work with. All right, in this problem, I am trying to work up to 72 groups of the 56. If I keep going 1, 2, 10, 5 at a time, it's going to take me a while. So what could I do to speed things up a little bit? Well, I like working with powers of 10 because then I can just do my place value patterns. And I see that I've got a 5 right here. I'm trying to get up to 72 groups. What if I figured out how many would be in 50 groups? That could be nice. That means that all I have to do, since I'm multiplying this by a power of 10 and multiplying this by a power of 10, all I really need to do is place another 0 on the end of what I had before. Nice. All right. 50. I'm trying to get to 72. Ooh, I could figure out how to get 20 more. I have a 2 already, which means 20, I would just place a 0 on the end there. Awesome! 1,120. Nice! Guess what, guys? You have everything that you need. Check it out. If we're trying to build up to this 72, look what we've got. 50, and then I have 20 more groups, and 2 groups. 50 plus 20 plus 2. That makes 72. Awesome! So that means that all I need to do is put together my total amounts in those groups, and I will have my final answer of how many would be in 72 groups. So let's add them up. You can use any kind of model that you want for adding. You can do arrow language, you can do the number line, you can do the traditional way. I'm going to do the traditional way just because I want to make sure that I am keeping track of all of my places, my place value. So we need to add our partial products together to get our final product. And our total that we get is 4,032. So we are ready to add the final group to our ratio table. 72 groups would have 4,032. There we go, there's my placeholder. 4,032. Final answer. Box up that final answer. Let's show how a ratio table could be used to solve the same problem, but instead of building up to 72 groups of 56, let's build up to 56 groups of 72. It'll give us some good practice with the ratio table, and it'll allow us to analyze and figure out which one's going to be the most efficient way for you. So when we read it like this basically means that we have 72 56 times, or 56 groups of 72. So let's set up our table. We never know how much space it's going to take, so I usually make it longer than what I actually need. You can always add on more later. And if I'm trying to get to 56 groups, well, a good place to start out with is 1. Let's think of our core 4. 1, 2, 10, 5. Okay, so 2 groups then of 72, we would just need to double it. So 72 doubled. Well, let's see, 70 doubled is 140. And then I can't forget about my 2 that I also have to double. That's 4 more. So 144. Awesome. Okay, let's do 10. Okay, so all I need to do is place a 0 if I'm looking at it as multiplying by 10, multiplying by 10, 720. And the last of our core 4 is 5. 1, 2, 10, 5. Okay, so let's chop that 720 in half. Well, 350 is exactly half of 700, and 10 is half of 20. So if I put that 350 together with the 10, I get 360. And that makes sense, because if we reversed the order and we went 5, double it is 10, 360, double it, we would get 720. So hopefully these are some things that you can start doing in your head, and just use the table to notate what you've done in your head. Okay, we have our core 4 finished. But remember, we're trying to build up to 56 groups. So we still have a ways to go here. So think to yourself, what might be another move? What might be the next move? Well, hey, if I'm trying to get up to 56 groups, I'm thinking that if I just place a 0 on the end of this 5, that gets me 50. And if I then do the same thing to the bottom that I did on the top, because we need to keep the proportions the same, the ratios the same, how they're related to each other, that would mean 360 multiply by a power of 10, place an extra 0. So now I have 50. Do I have 56 somewhere on this table? Oh yes. Oh yes, you do. You've got a 50, you've got a 5, you've got a 1. 50 and 5 and 1 makes your target group number 56. Sweet! So let's add them up. Let's add up these partial products. We have 3,600 plus 360 plus 72. You can do this traditionally like I have, setting up by place value. You can do arrow language in your head. You can use a number line. However you do it, you should get 4,032. And yes, I ran out of room over here. It kind of went off a cliff, but this is just showing that arrow language can figure it out too. What I would not do is I would not try to add the 72 in one step. That's very unfriendly. Think about how you could decompose the 72. Why do you think I decomposed it into a 40 here? Check out the compatibility. 40 and 60. I knew that that could be a nice friendly number that I could get to, and then I have the rest of the 32 to just tack on at the end. Okay, one last step in a ratio table. Fill in your final cell of the table. 56 groups would have 4,032. Now what I want to do right now is I want to, and final answer. What I want to do right now is I want to look at the difference between these two, and you can decide which way you like best. Our first method was 72 groups of 56. Looks like we were able to do a 50 and a 20 and a 2 for this one. And our second way was 56 groups of 72, and we were able to do a 50, a 5, and a 1 to make our 56. It looks like this way might have been slightly more efficient. We had friendlier numbers to work with. I usually like to pick the lesser of the factors, smaller of the factors, and build up to them in the groups and let my larger or greater numbers be at the bottom. That's usually how my mind thinks to do it, but sometimes it depends on the problem, and your mind might actually find it easier to flip it around. And that's the great thing about our friend, the commutative property. Yay! All right, here's one last example before your task for tonight's homework. 18 times 397, or you can think of it as 397 times 18. Either way, one thing that you should notice right away is that 18 is close to the friendly number 20, and 397 is close to the friendly number 400. So this time we might have some subtracting to do if we're thinking about this as 20 minus 2 groups, or this as 400 minus 3 groups. So that's something to keep in mind as you work. You don't always have to add up to the target. You could use some subtraction in there, and I want to show you what that might look like. So let's think of this as 397 groups of 18. Now usually I wouldn't do it that way, but this time, because I know that that's so close to a friendly number that I want, I can show you why that works nicely. So one group of 18 is 18. 2, double it. Core 4 here, 1, 2, 10, 5. 36. 10, just place a 0 on the end of the 1 group, 180. And 5, cut it in half, that's 90. Awesome. Check out what we've got here. I would really like to get to a group of 400 somewhere along the line. So what can I do in the meantime? Well, it might be nice to start with a group of 4, and then I can just place some zeros on it. Well, check it out. Double the 2 to get the 4. double the 36 to find out how many are in that group. So the double of 36, I like to decompose before I double. If it was just the double of 30, that would be 60. And then the double of 6 would be 12. So 60 plus that other chunk of 12 would get 72. Sweet. Now I can do 400. We have power of 100 here. So to get from the 4 to the 40, or sorry, the 4 to the 400, we multiplied by 100. So we'll do the same thing down at the bottom. Whatever you do to the top, you gotta do to the bottom, which means just placing 2 zeros for our place value patterns shortcut. Nice. Now, I know that 397 is not the same as 400. So this is not my final answer. I went a little bit past it. So I need to back up 3 groups. So I need to know what 3 groups of 18 would be. Well, check out what we have already. We have 1 group and 2 groups. Put them together. That makes 3 groups. So, in order to get my 3 groups, I need to look at my 18 and my 36, and I need to put them together to get the 3 groups. Just like we put the 1 and 2 together to get the 3. Make sure you're writing down all these arrows so that when you look back on your notes, you know how you got your information. We're going to figure out what 18 and 36 is. Another way that you could do it is you could say, well, 3 groups is 1 less than 4 groups, so I just need to take away a group of 18 from the 72. My mind likes addition a lot better though, so I'm going to go the addition route, but you could go the 1 group less than 72 route if you want to. And I'm going to get 54, hopefully in the correct color though. Now what I can do, don't need that 400 anymore. I've got it right there. What I can do is I can figure out, okay, so 397 groups would be the same as thinking about it as 400 groups minus 3 groups. So then our total must be 7,200 minus the 54 that are in those 3 extra groups. All right, so mental math, maybe using arrow language to show it. 7,146 for that final answer. Final answer. Okay, let's look at it reversed and see which one you like better. Okay, let's start with 1 group of 397. We're trying to get to 18 groups. 2 groups of 397. It's already getting kind of ugly. 794 after I think about it for a while. Okay, 10. Oh, phew, I can just work with zeros here. 3,970. And a 5. Oh man, I have to cut that in half. Cut the 10 in half and get 5. Cut this in half and get 5. My core 4 is turning out to be a lot of work. Maybe I can skip it. Maybe I don't need the 5. Maybe I can go back and do that step if I want to later. For now, I'll just leave it blank because that's not very friendly. Let's see. What about a group of 20? Because 20 is really close to 18. Well, 20, I can look at my 2. Just place a 0 at the end because I'm multiplying by a power of 10. Ooh, I think I've got what I need. I don't need the 5. If 18 is like 20 minus 2, then I should have what I need for 18. Looks like all I have to do is one quick subtraction problem. Yep, got the same answer. 7,146. Final answer. Sweet. So, which one did you like better? Working up to 400 groups and then backing off 3? Or working up to 18 groups and then backing off, or working up to 20 groups and then backing off 2? Each has its advantage. This particular one that we're looking at now, not very friendly when it comes to doubling and halving with 397. 18 in my mind is more friendly to work with, but we were able to make this work really nicely too. So ultimately you have to choose what's going to work the best for you when you use the commutative property. Yay! All right, here's your task. Solve 126 times 23 using a ratio table. Some things to remember. Ratio tables are a way to organize number strings. Look for places that you can use doubling, halving, or powers of 10, those place value patterns where you just cheat with zeros. And whatever you do to the top, you have to do to the bottom. Hopefully we'll have lots of different ratio tables out there depending on how you choose to solve this problem.